Welcome to my class. I'm Drew Collop. In today's class, we're going to talk about dilutions. This will be the first of 2 lectures on dilutions. In today's lecture, we'll talk about dilutions, and in the next lecture, we'll talk about serial dilutions. So what is a dilution? When we're diluting something, we're reducing the concentration of the solute by mixing it with more solvent. When working in a lab, chemicals are often purchased as pre-mixed high-concentration solutions. You must dilute them down in the lab to the desired concentration in order to use them. In addition, making up fresh solutions every day can be very time-consuming. You have to weigh the chemical, dissolve it, potentially titrate it, filter it, autoclave it, many different steps along the way. It may be more efficient to make a stock solution, a higher concentration solution than you require, but a large volume of that. You can then dip into that stock when required and then dilute it down to the desired concentration. In any case, performing a dilution is a critical skill to have in any laboratory. Let's examine a very simple dilution. We want to make a 10 ml solution. We're going to dilute down a stock solution. We'll take 1 ml of that stock solution, a more concentrated version, and we'll dilute it down by adding 9 ml of solvent to that. Now please note, there's a difference between ratios and fractions. I can represent this dilution as 3 different ratios. 1 to 10, representing 1 part stock to 10 parts total solution. I can also represent the same dilution as 1 to 9, 1 part stock to 9 parts solvent, or 9 to 10, 9 part solvent to 10 part solution. However, as a fraction, the denominator is always going to be the total amount. Total amount of solution on the bottom, and your stock is on the top. When discussing dilutions and writing them in fractional format, there should be no miscommunication. On the top, we're talking about the solute. On the bottom, we're talking about total solution. The issue with dilutions is when we express them as ratios. Once again, all these 3 things represent the same process. As a result, you must define what those values are in a ratio, because in a ratio, we can have whatever we want on the left side and right side. To make sure there's clear communication, define those values. Many a time, a student has come in the lab and been told to do a 1 in 10 dilution. What you would do is you would add 1 part stock solution and 9 parts solvent to make a total of 10 ml. This is sometimes not what happens. Student hears 1 in 10 dilution, they take 1 part stock solution, solute, and they add 10 parts solvent, making a total solution of 11 parts. Consequently, this solution will be incorrect as it will be too dilute. So as a reminder, make sure you define your values if you express a dilution as a ratio. Let's look at a simple example here. Suppose you have a solution containing 4 microliters of sodium chloride and 100 microliters of water. What is the ratio of sodium chloride to water? Notice I defined that. I'm going to talk about the ratio of sodium chloride compared to water. I can write that as 4 parts sodium chloride to 100 parts water. I can then simplify that down to 1 to 25. If I use a different ratio, comparing sodium chloride to total solution, I will get a different ratio. In this case, I would get 4 parts sodium chloride to total solution. I add my solute plus my solvent, 104. Notice the ratio is different. Last question here, what's the concentration of my final solution in percent volume by volume? Well, remember, percent volume by volume, I'm going to have mils on the top and mils on the bottom. My solute is on the top, 4 microliters of my solute, which is sodium chloride. And on the bottom, I have my total solution. Microliters cancel microliters. Notice here our final answer will be in milliliters. We can cross multiply. Divide both sides by 104 to isolate x on its own. Significant digits. Notice, I've told you how many significant digits I would like in the final answer. So we'll round this off to 2 significant digits. X is equal to 3.8% volume by volume. Final answer. So once again, if you write your dilution as a fraction, there's no miscommunication. Fractions are always talking about solute over total solution. With ratios, however, you must define which is which, because you can have total solution compared to solvent. So there can be confusion. So when working in ratios, make sure you define. Let's look at the next example. How much water needs to be added to 8.5 mils of stock solution to make a 1 in 20 dilution? So my new solution is going to be 20 times more dilute. So I'm going to take my stock solution, 8.5 mils of my stock, and I want to make it 20 times more dilute. So to get the final volume, I'm going to divide by 1 over 20. If you divide by a fraction, you flip it and you multiply it. As a result, the final volume will be 170 mils. The question asked how much needs to be added to this solution. So I can take my 170 mils of my final solution and subtract away my 8.5 mils of my stock solution. This will then give me 161 mils of my solvent. So I can take the stock solution, I can add 161.5 mils of water to that, and this will make the new solution 20 times more dilute. Example 4. What is the dilution if 45 mils of stock solution has 270 mils of solvent added? So my stock solution, my solvent, was 45 milliliters. I'm going to add to that 270 mils of my solvent. Now remember, when we're talking about fractions, we're talking about total solution. So I have to add that stock solution onto the bottom. Add those up. Mils will cancel each other out, and we can simplify this fraction down to 1 over 7. So if I took 45 mils and I added 270 mils of solvent to that, my final volume would be 315 mils, and it would be a dilution of 1 over 7, 7 times more dilute. So as you can see, with dilutions, we're taking a higher concentration solution and making it a lower concentration solution by adding in a solvent, which is usually water. Now, going back to one of our earlier lectures, we talked about a mixture of solutions. We took the concentration of one solution, we added another solution with a different concentration. When I combined those together, I had a final volume. With dilutions, we're adding in a solvent. Usually, it is water. If this is my stock solution, it has the concentration of some chemical, which is not water. If I add water in, what's the concentration of that chemical in water? Well, if it's pure water, the concentration of that other chemical would be 0%. As a result, your concentration is 0. Anything times 0 is 0. So notice, this would just be removed from the equation entirely, giving me so this is a modified version of your mixture formula. C1V1 equals CFVF. So this is for dilutions when you're adding water in. Let me show you in further detail. 35 mils of the first solution, which is 25% weight by volume sodium chloride, is mixed with 65 mils of a second solution, which is pure water. What is the new concentration? Let's use the initial formula, C1V1 plus C2V2 equals CFVF. We'll sub in our values here. Your first solution, 35 mils, 25%. Weight by volume, multiply by the volume, 35 mils. We're then going to mix that with 65 mils of my pure water solution. So my concentration of sodium chloride in pure water will be 0%. My volume, 65 mils. Finally, we will get a final concentration, and our final volume will be the sum of these two values here. So notice right here, this value here, 0 times 65 is just 0. As a result, these terms are not required in a dilution calculation. So just to try and reiterate, for dilution, you could remove the C2V2. Let's now solve that same problem without the C2V2. It's exactly the same. 25% weight by volume, C1V1, 35 mils. And that's equal to CF times our 65 mils pure water plus 35 mils of my stock solution. Rearrange and solve. $65 plus 35 is 100. Mils cancel out. I'm left with 8.75% weight by volume. Final answer. Notice significant digits. We have 3, 3, 3. When we add those together, technically there would be another digit there, but we're going to round off to 3 significant digits. One thing to take note is your VF. Because we removed the C2V2, V2 won't be in the formula. So you'll have to add up your V1 and your V2, even though V2 won't be in the equation anymore. Don't forget that. Let's look at another example now. Suppose you have 1 liter of stock solution containing 0.3 molar acetone, but you want a solution containing a lower concentration, 0.03 molar acetone. What should you do? Well, let's do our C1V1 equals CFVF formula. I have my volume of my stock solution, it's 1 liter. I have the concentration of my stock solution, and I have the concentration of my final solution. What I don't have is my final volume. Let's rearrange it. Sub in our values. Units will cancel. 0.3 times 1 divided by 0.3. This will give me 10, and my units are liters. Now please note, this is VF, my final volume. As a result, I have to take that final volume and subtract away my stock volume. This will give me 9 liters of my solvent. Therefore, add 9 liters of solvent to 1 liter of stock solution. This is how you would dilute this solution. Let's examine another question. How much stock solution would be needed to prepare 10 mils of a 2 to 5 dilution? So what information do we have here? This is my V1. I need to prepare 10 mils. That's my VF. Here is my dilution. My dilution is 2 to 5. 2 parts stock, 5 parts total solution. So to find out how much I need to start with, my V1, I can use this as a conversion factor. Given I want 10 mils of my total solution, I'm now going to convert from total solution to stock solution. We have 5 parts total solution for every 2 parts stock. Parts cancel out, solutions cancel out. I'm left with milliliters of stock solution. 2 times 10 is 20, divided by 5 is 4. Units are going to be milliliters of stock solution. Therefore, we will add 4 mils of stock solution with 6 mils of solvent, usually water, for a final volume of 10 mils. So this is how you would prepare 10 mils of a 2 to 5 dilution of a stock solution. Let's now look at another example. Stock solution, something called cupric sulfate, 7.0 weight by volume. How much stock? This will be my V1. Would be needed to prepare 25 mils. It's going to be my V2 of a 1 in 50 dilution. Also, what is the concentration of this newly diluted solution? I'd like you to pause your video and give this a try right now. I will then take it up. Let's take it up. So I need to know V1. I have V2. Write that down. 25 mils, my final solution. I will then convert 50 parts solution for every 1 part stock. Again, we're getting that from our dilution rate here. Solutions cancel solutions, parts cancel parts. I'm left with milliliters of stock. So this will then tell me I have 25 divided by 50. It's going to be 0.5 milliliters of stock. Therefore, to make this up, mix 0.5 mils stock with 24.5 mils solvent. The second part of this question was, what's the concentration of this new solution? C1 V1 equals CF VF. I know my concentration, 7%. I know my initial volume, 0.5 mils. And I know my final volume, 25 mils. What I don't know is my final concentration. Rearrange before we sub in. And then sub in and solve. Notice my units are in the calculation. Mils cancel mils, and my final units will be percent weight by volume. 7 times 0.5 divided by 25. Final solution, 0.14% weight by volume. I would like you to pause your video and try this one as well. How much solvent would be added to 20 mils of stock solution of an 8% solution of weight by volume of Janus Green B to prepare a 5% solution? So we're diluting from 8% to 5%. Pause your video, try this now. Let's take this up. C1V1 equals CFVF. Again, this is our dilution formula. I'm given concentration 1. My initial concentration was 8%. I'm given my final concentration of 5%. I'm given my initial volume of 20 mils. What I don't know is my final volume. But I asked for how much needs to be added. So I'll have to do one extra step at the end. Let's rearrange first and then solve. We're solving for VF. Sub in now. Percent weight by volume cancels out. I'm left with milliliters. 8 times 20 divided by 5. 32 mils. Now this would be my final volume. I didn't ask for that. I asked for how much do I need to add to the stock. As a result, I take my 32 mils total solution, subtract away my 20 mils stock solution, and this will give me 12 mils of my solvent. Therefore, add 12 mils solvent to 20 mils stock solution. So as you can see, when we're diluting something down, we took that C1V1 plus C2V2 equals CFVF formula, and we got rid of one of the solutions. Why? Because we're diluting with water. And water, if it's pure, will have 0% concentration of the chemical you're diluting. Consequently, that is removed. We can then just use C1V1 equals CFVF. Just be careful. VF will be V1 plus V2, and V2 now won't be actually written into the formula. So just be careful of that. One last question for today. We start with the story. This story comes from many years ago. An instructor was teaching Bio 273. They were having the students perform a dilution, a 1 in 1 million dilution. The professor gave the instructions to perform it, and then the students got to work. However, one student meandered about, wandered around the lab, looking for something. The professor observed the student and just watched them. Couldn't figure out what was going on. Eventually, the student came over to the professor and asked, "Excuse me, where's the 1 million milliliter beaker?" Perplexed, the professor looked at the student and then suggested they continue to search for it. Eventually, the student figured this out. We don't have any 1 million milliliter beakers in our laboratories. You could theoretically have one. It would have the dimensions of 1 meter cubed. Now, theoretically, if you were doing a 1 in 1 million dilution, theoretically this would work. We could take 1 milliliter of our stock solution and add in 999,999 mils of our solvent. That would work. 999,999 milliliters of solvent. And we add to that 1 mil of stock. Now on paper, that will work. In practice though, not a chance. There's no way this person will be accurate with their dilution. A few problems with that. Number one, where you're going to get the beaker from. Number two, how are you accurately going to measure 999,999 milliliters of solvent? When measuring liquid, we always recommend doing it in a single step. If you have to do multiple steps, you introduce human error every single time. Also, how are you going to mix this? I guess you could get a paddle on a drill and you could spin it around and mix it, but again, that's not very practical. However, a 1 in 1 million dilution is a common dilution to be done in many, many labs. So the question is, how do we do this? Well, we don't do a single dilution. We do a serial dilution. And that will be the topic of our next lecture. So in today's lecture, we took C1V1 plus C2V2 equals CFVF. And because this is going to be water, the concentration will be 0%. Consequently, C1V1 becomes C1V1 equals CFVF. This is for dilutions. This is for mixtures. I would also advise you to rearrange the equation first before subbing in. In the next lecture, we'll continue on with this discussion, discussing serial dilutions. That's all for today. Until next time.